Now let's talk about the side-splitter theorem. A segment drawn between two sides of a triangle, parallel to the third side, will form a smaller triangle that is similar to the original. So we are given triangle ADE in our diagram, and through point B we draw the segment BC such that it is parallel to segment DE, and this makes triangle ABC, and it is similar to triangle ADE. A segment drawn parallel in this manner splits two sides proportionally, so that in our diagram the lowercase variable r to the lowercase variable s is equal to the lowercase variable t to the lowercase variable v. In other words, the measurements of these two sections of one segment make the same proportion or ratio as the two smaller segments that make up the other side that gets split. We're going to start off with the first part of the side-splitter theorem proof, proving that the triangles are similar. Let's get started with the side-splitter part 1 proof puzzle. We're given that segments BC and DE are parallel to one another, and we need to prove that triangle ABC is similar to triangle ADE. Well, with any proof, whether it's flow proof, paragraph proof, or two-column proof, we always start off with what is given to us. And we are given that segment BC is parallel to segment DE. And now that we have parallel lines, there are different pairs of angles that are congruent to one another with parallel lines. They could be corresponding, they could be alternate interior, and they could be alternate exterior. So we have, for example, angle ABC, and it would be congruent to angle ADE because they are corresponding angles. They are in the same corresponding position in that upper right-hand section of the parallel lines and transversals. So therefore, these two angles are congruent. Okay, next we can look at the similar triangles statement that we need to prove. We have triangle ABC and triangle ADE. They both have one common letter in them, angle A. So we can say that angle A is congruent to itself by the reflexive property of congruence. And a trick for using the reflexive property is if your triangles or your shapes that you are trying to prove are similar or congruent have the same one, or if they have the same one letter in common, then they will share a common angle. If they have two common letters, then they would end up sharing a common segment. So if we compare ABC and ADE, they both have an A in them, and we can see that the smaller triangle has an angle measured at A, and so does the larger triangle. It has that value at angle A, and any angle is congruent to itself. And now, since we have two angles labeled as congruent in both our small triangle and large triangle, we can say that these two triangles are similar by the angle-angle similarity theorem. Now let's prove part 2 of the side-splitter theorem. We're going to start with the same given statement that segment BC is parallel to segment DE, and that's given to us. And we just found out that triangle ABC is similar to triangle ADE by angle-angle similarity, and we just proved that on the previous slide to prove that the side-splitter theorem part 1 is true. So now we can jump right from the given to this similar triangle statement by the side-splitter theorem part 1. And now that we have similar triangles, we can write down side length ratios in each triangle. So for triangle ABC, we can say that the ratio of AB to BC to AC is equal to the ratio of the corresponding segments in the larger triangle. So AD to DE to AE. Notice we went left, bottom, right in both cases, left, bottom, and right. So next what we can do is we can create a proportion with any pairs of sides that are proportional to one another. So we can say that AD to AB, both of the left sides, or both of our first values, is equal to, and we went large to small, so we would have to do AE to AC in the other one, and that's by the property of proportions. When you have your definition of similar triangles, you can take your ratio of three sides and write them in proportion. So now, since we're looking for BD, that's the smaller part that's not currently in here, and CE, these two at the very top, or the first values in our proportion, or in our fractional sides of the proportion, we can rewrite AD as AB plus BD by the segment addition postulate. And we can do the same thing for AC plus CE equals AE. We're using the segment addition postulate twice. You could either write them as separate statements like 5 and 6 and write the segment addition postulate as the reason 2 times in a row, or you could list both of these under one statement and write down the postulate one time. It's entirely up to you. The next thing that we can do is, since we know that AD is equal to AB plus BD, we can take this section of the segment addition postulate and substitute it in for AD in this proportion. And similarly, we can take AC plus CE and substitute it in for AE in the proportion in order to get AB plus BD, all divided by AB, is equal to AC plus CE, all divided by AC. Again, all we did was we took the two smaller segments that add up to the larger one and substituted them in for the larger segment on each side of our proportion. And the next step that we can do is we can rewrite, and I'm going to write it up here where I have a little bit more space. We have AB plus BD over AB. We can rewrite this as AB over AB plus BD over AB. Because whenever you had, say, 1 plus 2, all divided by, say, 5, you could rewrite it as 1/5 plus 2/5, and you would get 3/5 in each case. So we're using that same property of fractions, and we can then simplify AB divided by AB to be 1, and then plus BD over AB. So we're going to get 1 plus BD over AB, and then using similar reasoning, we can rewrite AC plus CE all over AC as AC over AC plus CE over AC, and then AC over AC is 1, that's where we're getting this value from, plus CE over AC. And the reasoning behind it is an arithmetic fact, or a property of fractions. And now notice that step 7 has a 1 on both sides of the equation. So if we subtract 1 from both sides, we will end up getting BD divided by AB is equal to CE divided by AC. And again, we did that by subtraction. We subtracted 1 from both sides of the equation. And this is the statement that we needed to prove. So this proof has been completed.